All right, so this is going to have a different flavor. Right, it's going to click again. Yep. Okay, so I already showed you this slide just to point out that we covered this part. And now to understand PVS potential for BSM searches, one must have general knowledge about worldwide BSM efforts, especially as it relates to violation of symmetries. Okay, so I'm going to start off by showing you my classification of the 4 classes of measurements worldwide, then talk about neutrino physics, discrete symmetries, and a tour of searches for violation of what I call accidental symmetry. Okay, so this is our standard chart. These are kind of the same kind of questions I put down before. I want to put this up here because this is our current knowledge. It's like a wall chart. But also, there are these 2 color-coded questions. These are typically funded by particle physics. This is typically funded by nuclear physics. But I want to argue, I think the DOE has finally figured it out that this is an artificial separation. Okay, so the intensity frontier. So this is the focus here. This is my classification, neutrino properties, search for violation of accidental symmetries, direct and indirect searches for dark matter. I believe you're going to have a topical lecture on this next week. So I will say very little about this, but I will just motivate it at the end. And then this will be the topic for tomorrow. Okay, neutrino physics. So first of all, I want to put this up. This is the entire content of this famous paper that got him the Nobel Prize. Okay, this is the model of leptons. Why do I put it up here? I want to point out all the charges. So this is already done in the previous lecture. If you look at the charge assignments here, you have the neutrinos with no charge. And then you have the weak isospin, the right-handed neutrino with no weak isospin. And then given this formula, which is in this paper, you have the hypercharge for the right-handed neutrino is also 0. So 0, 0, 0. Right? So the right-handed neutrino has no gauge interactions. So this was all fine with Weinberg because the neutrino is massless. Right? So who cares? So there's no right-handed state anyway. So this was the original formulation of the standard model. And I want to emphasize one thing here, that this right-handed neutrino, especially the neutrinos in general, everyone knows the Higgs is a special particle. It is the massive spin-zero particle that was just proposed by theorists, and we found it. But the fact that you have a matter particle, spin 1/2 particle that has no charge is equally amazing for various reasons that I will go to. And in some sense, maybe even more important than the Higgs boson. So now we know that neutrinos are massive. Okay, so I will only show this plot, which did not win the Nobel Prize from Kamland, because it's the easiest one to show. A lot of us think that they should have been included in the Nobel Prize. This is the Kamland experiment showing you a data points, and all you need to know is that if there was no neutrino mass, this would be flat. That's all you need to know. I'm not going to go into any more detail. Okay, this is not flat. Neutrinos are massive. That's it. So neutrinos are massive. Why are neutrinos so light? What is the mass scale? We don't know the absolute mass scale, which I will tell you in the next slide. How is neutrino mass generated? We think there is the Higgs mechanism, of course, but is that all? There is a neutrino mixing matrix. Is there neutrino CP violation? Are neutrinos Majorana particles? These are important questions. Typically, this kind of plot is shown. This is a log scale. These are all the masses of the charged fermions. And we know that neutrinos are sitting here. And there seems to be this gap, right? So neutrinos seem special in many ways. So anyway, my main thing though here is there must be right-handed neutrino states. So this is kind of interesting about, are they just sterile? Why are they there? Okay, so this is the one slide I have on neutrino properties worldwide. There's a lot of physics here already. So first of all, remember that once you have neutrino mass, you have neutrinos of definite flavor. And then these neutrinos of different flavor are superpositions of the mass eigenstates, nu1, nu2, and nu3. And so there is a matrix that takes you from the flavor eigenstates, the mass eigenstates. This is the PMNS matrix, the unitary leptonic mixing matrix. So as soon as you have a mixing matrix like this, experimentalists ask for money to try and measure every component matrix. So that is certainly what is going on here with all of these experiments all over the world. There's another subtle thing, which is that because we have only observed neutrino oscillations, we only have 2 delta m squareds. We don't know which delta m squareds they are. We know that it's this one, we have these 2 measurements, but as to whether this delta m squared, the small one, the so-called solar delta m squared, is here or here, we don't know. That makes a huge difference because there's a big order of magnitude difference between atmospheric delta m squared and the solar delta m squared. And so this is called normal. This kind of is more natural, one thinks, but nothing is natural with neutrinos, so we have no idea. And this is called inverted. Okay, so we don't know. So we don't know this, we don't know, we know a lot about this mixing matrix, we don't know everything. Okay, so this is a huge program, mostly funded by high energy physics. Okay, so there are other neutrino initiatives, so I only have one slide on it, just so you are aware of these things. There is a new process that is being now measured by dark matter experiments, coherent neutrino scattering, which is incoming neutrino scatters of a nucleus. There's a lot of nuclear physics that goes into this, but primarily it's about trying to measure neutrino interactions in a new regime. So the main reason we are able to do this now is that the recoiling nucleus can be observed by dark matter experiments that are near reactors, for example. So a larger number of are pursuing both accelerators and reactor-based measurements for a range of nuclei. So you need a ton scale these nuclei to be sitting there, and then you watch neutrino interactions. So new exploration of tens of MeV inelastic neutrino scattering. And this has relevance to understanding the neutrino axial current to nuclei, for example. And then there's absolute neutrino mass. So, right, so when you do oscillation experiments, you don't get the absolute neutrino mass, you only get mass differences. So the precision endpoint of beta decay spectrum is still being pursued. There are all kinds of reasons cosmologically that you want to know what the absolute neutrino mass scale is. So Catherine will be completed in the late 2020s, and they will get down to 200 milli eV. The next frontier is getting down well below 100 milli eV with Project 8, and there are complementary efforts using other nuclei as well. All right, so that's all I'm going to say about the various neutrino, except I'm going to spend a lot of time on one compelling theoretical and experimental reason why neutrino mass is so amazing. And so to do that, I'm now going to take a detour to discrete symmetries. So now let's get back to some basic physics. So let's come back to parity, right? Parity is a discrete symmetry. It is a group of 2 elements. And if the Hamiltonian is invariant under parity transformations, then this quantum number is conserved and it's observable. So until parity violation was discovered, parity symmetry was considered to be a good quantum number. And when people started to measure new particles, a parity was assigned to them depending on its invariance properties. Likewise, another discrete symmetry is charge conjugation. Charge conjugation takes particles to its antiparticle, flip sign, all quantum numbers flip sign except mass and spin. Okay, particles that are its own antiparticles are eigenstates of C, and this can be used. For example, C on the photon is minus the photon wave function, and so pi 0 to gamma gamma is allowed because of the quantum numbers of the pi 0, but pi 0 to 3 gamma is forbidden. Now, of course, you can find other reasons to show why pi 0 to 3 gamma is forbidden, but this is one argument. So this is just to show you how these symmetries are used. Now, then in the early 50s, they ran into a problem. Why was parity violation even proposed? If they found a particle in 1956, and they gave it a name. It decayed to pi plus pi 0. And because it decayed to pi plus pi 0, its parity was considered to be plus 1. And so it was called this was called a theta plus. And then the tau plus was pi plus pi 0, and this has a parity of minus 1. So they were confused. You have the exact same mass, opposite parities. What's going on? So this is why Li and Yang proposed that this is the same particle, because they originally, the PDG in 1956 assigned them to be two different particles. The same particle is produced in strong interactions, but decays by the weak interaction. P is conserved in strong interactions, but not in weak interactions. This was the proposal, and this was the reason for the proposal. Okay, so instead of, then I will go through this parity violation, and so that's why Madan Wu did the experiment, V minus A, blah, blah, blah. I already went through this, so I'll skip this. But now I'm going to take a detour, even though it's completely irrelevant. Well, it's somewhat relevant to the things I'm going to talk about in the rest of the lecture. But it's very important for you to understand the extraordinary simplicity and brilliance of the original CP violation discovery. I want to walk you through that, okay? So we now know, because we know about quarks, that the theta plus and the tau plus is the same particle. It's the K plus, and it's S bar U, okay? And so there's also the K minus, which is SU bar. And then you have the K0 and the K0 bar, S bar D and SD bar. So in 1956, we didn't know about all of this. So the question was, they have opposite strangeness, but are they distinct? Right? So if you're going to say that you can have opposite parities, or what opposite strangeness? Are they distinct? So there was this brilliant, absolutely brilliant proposal made by Gell-Mann and Pays. Assuming CP conservation, they proposed the following experiment, which was immediately done. So first of all, you apply the CP operator to, when you apply the CP operator, you take a left-handed particle to its right-handed anti-particle, right? So if I take it to the electron neutrino left-handed, you apply the CP operation, you will get the right-handed anti-neutrino, right? So let's do this to the chaos. They proposed to make linear combinations of the K0 and the K0 bar and call this one K1, and then this combination the K2. Why would they do that? Because if I now do a CP operation on K0 bar, I get K0. If I do a CP operation on K0, I get K0 bar. And therefore, if I do the CP operation on K1, I get plus K1. If I do the CP operation on K2, I get minus K2. Therefore, K1 can only decay to 2 pions, and K2 can only decay to 3 pions. Now, why is this? Given the mass of the K plus, the 3 pion decay is extraordinarily long compared to the 2 pion decay because of phase space. Okay, once you add 3 pions, it's almost the mass of the K plus. So there isn't much phase space. So you get a very long lifetime. So this 3 pion lifetime is much longer. So they realized that the K2 will have a very long lifetime, K1 will have a short lifetime. So if CP is conserved, K1 to 2 pion is allowed, K2 to 2 pion is not, 3 pion is not, K2 to 3 pion is allowed, but K1 to 3 pions is not allowed, K2 to 3 pions is not allowed. Okay, so here's the experiment. You take a K0 beam, which they knew how to make, and the K0 now is a linear combination of K1 and K2, because that's how you constructed it. So there are K1s and K2s, Now you let this go for a while, and all the 2 pion decays will go away. And there will only be 3 pion decays left. But we know that if it's only 3 pion decays, it's K2s. So you started off with K1 and K2s, you're only left with K2s. And that means you got K anti-Ks now. Because if I have K2 quantum state, it has both K0s and K0 bars. So you started with K0s, and you ended up with K0 bars. This is called strangeness oscillations. This was the first spectacular quantum mechanical demonstration of oscillations, right? So just the appearance of K0 bars after a drift region is quantum mechanics at work, right? Okay, so now here is the experiment is not done. The K0 bars have much larger cross section to scatter off nuclei. And so now, if I take the K2 beam and you put material in front of it, I will remove all the K0 bars and I will end up with just K0s. That means I took K2s and now I have K1 again. And so if I put the material in, I will see 2 pion decays again. It's an amazing thing, right? So you started off here, drift region, anti-kaons, you put material, boom, 2 kaons again. Even though you've drifted a long way, you've suddenly generated new K1s. And so you have 2 pion decays again. So it's a brilliant thing to test. And so it was done. So K2s, anti-kaons only, the second part, you put material, K1s again, 2 pion decays. But here's what happened at the experiment. And they did discover this by accident. They removed the material, and they still saw 2 pion decays. Okay, so let me go back to the previous slide. Very important to realize this. And imagine that everybody's told you CP violation is sacrosanct. And you're looking for 2 pion decays again. You take this material, you remove it, and it's still there at a lower level, but it's still there. Imagine you are this experimentalist, and you are willing to publish this when this was considered impossible. Right? You have to have done all kinds of tests. And this is what Cronin, Fitch, and Tourlet did in the early 60s. They got the Nobel Prize for it. So, so we now know that the K long is mostly K2, but a small admixture of K1. And the K short is mostly K1 with a small admixture of K2. So I show this as how looking for symmetries and symmetry violations is an extraordinarily powerful way to make new discoveries. Okay? All right, so now that CP violations we discovered, there was a big deal about matter-antimatter asymmetry. CP violations requires 3 generations of quarks. It also explained why we needed 3 generations of quarks. It has a complex phase now. However, we now know that the electroweak CP phase does not explain all of the matter-antimatter asymmetry. So it's still an open problem, but this was a pretty important deal because of the Sakharov criteria for the fact that you need CP violation for the matter-antimatter asymmetry. Okay, so now let's go on to symmetries again. Are there other symmetries at low energy? Are they exact? If they are approximate, were they unbroken in the early universe? So if I have something like electric charge, then you have the sum of the initial charges, sum of final charges. So this is an additive conservation law. So for example, it shows you why proton decay is highly suppressed. Lucky for us, otherwise we wouldn't exist. But of course, we know baryons are made of 3 quarks, and it is kind of incorporated, this kind of baryon number conservation is incorporated in the standard model. So just to emphasize, conserved electromagnetic current leads to charge conservation, which is an additive conservation law because charge happens to be quantized. And similarly, the standard model Lagrangian is invariant under other phase transformations, just like charge associated with total baryon number and total lepton number. Okay? And this brings us to baryon and lepton number. Are they exact symmetries or not? We don't expect them to be for various reasons. So I already showed you how baryon number you look at. This is forbidden because if you start with a baryon, you should end up with a baryon. Then there's lepton number. So this is important to understand with the weak interactions. If I start with a pi plus, I will end up with a mu plus and a muon neutrino. And then if you take that muon neutrino that is produced by the pi plus beam after it decays, and I have that interact with matter, so nu mu times n, I will make a mu minus. I will never make a mu plus. So if I start with a pi plus beam, I will end up with a mu plus and with a mu minus, but never a mu plus. Okay? To force this to be true, you have to introduce something called lepton number. You assign the +1 to the electron and the electron neutrino, and the -1 to the positron and the antineutrino. And this is encoded in the standard model Feynman rules. Okay? But only B minus L is strictly conserved in the standard model. B plus L is violated due to anomalies. So there is no fundamental reason for B and L to be independently conserved, assuming there are no new forces. So is there another way to explain it instead of forcing lepton number to be conserved, this kind of observation? And that is why parity violation of the weak interaction comes in. Neutrinos only interact via the weak interaction. So the pi plus makes a new left because in the rest frame, you can just show that if I make a mu plus, I must make a new L. And then the new L has to make a mu minus, and that all comes from the left-handed projections, right? And therefore, the right-handed right-handed projection will give you a mu plus, and so on. So there is no reason to force the standard model Feynman rules to have lepton number conservation so long as you have the V minus A weak interaction. Okay, so you don't need lepton number conservation to explain everything that you see. So this brings us to double beta decay. All right, so this is a profound question now that you have a massive neutrino and the fact that you do not need to have lepton number conservation. In 1937, Majorana discovered that a simple modification to Dirac equations, it's possible to describe electrically neutral spin 1/2 particles with real fields. And the moment you have real fields means you don't need an antiparticle. And so the neutrino can be its own antiparticle and still not break any fundamental laws. But that moment it is its own antiparticle, then lepton number is violated, right? So if you have a Majorana neutrino, lepton number is violated. There is no experimental observation. This is impossible to do with neutrino interactions. Okay, there are all kinds of reasons I won't go into, except for double beta decay, which we'll come to in a minute. So the conceptual question of whether the neutrino is Majorana or Dirac is a cartoon that I stole from Boris Kaiser. Take a left-handed neutrino, apply the CPT operation to it, and you will end up with the right-handed antineutrino. If I do a Lorentz boost on a massive neutrino, I can go from right to left-handed. I already explained that before, right? So this is the way I can end up with a left-handed antineutrino. But if I just do a Lorentz boost to a left-handed neutrino, do I end up with the right-handed neutrino or whether do I end up with this Lorentz boost? Do I end up here? Or with a Lorentz boost, do I directly get the right-handed neutrino? This is the question. In this case, there are 4 Dirac particles. In this case, there are 2 Majorana particles. The question is whether when I do a Lorentz boost on a left-handed neutrino and a CPT transformation on the left-handed neutrino, do I arrive at the same particle or 2 different particles? That's the question. The most pragmatic approach to discover this is to search for lepton number violation, right? The moment you have lepton number violation, it means there are Majorana neutrinos. And practically, it means neutrinoless double beta decay, which I'll explain. So if lepton number is observed unambiguously, it implies there exists a way to convert an antineutrino to a neutrino, Majorana mass amplitude. And that also immediately means a new heavy scale for new physics. Okay, the moment you show Majorana particle, people might argue that we still haven't broken the standard model because it just have massive neutrinos. But if you have Majorana neutrino, you're broken the standard model. Okay, so if you have a Majorana neutrino, then just to remind you, in the Lagrangian, you actually can construct this. I won't go into the details of this. You can stick in a term in the Lagrangian because you don't need, if you decide you don't need to have lepton number conservation, you can add these terms to the Lagrangian. Once you do that, one limit is that the heavier mass here goes to 0, and then you get the Dirac neutrino, purely Dirac neutrino. So most of us believe that neutrinos are Majorana because it's actually the less demanding choice. Because if this goes to 0, you're demanding there be lepton number conservation in the electroweak Lagrangian for no good reason. Okay, so this is not the most conservative choice. Another limit is to have a very heavy so you don't see it nowadays. And then the light state, so-called seesaw mechanism, it gives you a natural reason for why neutrino masses are light. So if you have Majorana neutrinos, you have two self-conjugate states. You have a natural explanation for light neutrino masses. And also, it gives you a new avenue to add to CP violation, because when you have lepton number violation, then you also have baryon number violation, and then you end up with a new source of getting matter-antimatter asymmetry in the universe. Okay, so it's very attractive to try and see whether neutrinos are Majorana. So double beta decay. So first remind you what the beta decay is. So beta decay, first of all, when you have just a free neutron decay, you make an electron and an antineutrino. If you do this in a nucleus, then a neutron converts to a proton in the nucleus. You go to the next element in the periodic table. If I look at this iodine 136, for example, and you look at xenon 136 here, beta decay would take it to cesium 136. But in fact, cesium 136 happens to be, due to the nuclear pairing force, heavier than xenon 136, so it cannot decay by single beta decay. However, quantum mechanically, it can tunnel through and simultaneously emit two Ws and go straight from xenon to barium. Okay? And that is the so-called double beta decay process, where this is virtual here in between. And this was already suggested in 1935 by Maria Goppert-Meyer. So, candidate nuclei with Q greater than 2 MeV. The reason for that is otherwise it's too hard to discover. These are all, most of these have now been observed in experiment. Maybe 2/3 of these have been observed in experiment in double beta decay candidates. Okay. So this is ordinary standard model lepton number conserving double beta decay. Okay, so now to motivate double beta decay, let's do another Gedanken experiment as a theorist. If I take E plus E minus, E minus E minus, I make a collider with just two electrons colliding, there should be a probability to make two Ws. But of course, that will violate lepton number. And you must have massive neutrinos because you need both helicities here for this to work. So this cannot carry a lepton number, and it must be massive. Okay? This is, of course, possible. But if you calculate the cross-section, even if you built an E minus collider, you just don't have enough luminosity to see this. Okay? It'll be a ridiculously small cross-section. Okay, on the other hand, if I take this diagram and make the two Ws virtual and attach it to a nucleus, the same diagram, Avogadro's number helps you. When you have such a large number of nuclei, it is possible to observe this. This is called the neutrino mass mechanism for double beta decay. Okay, this diagram being just a virtual neutrino. So the experiment is simple. You take a double beta decay nucleus and you look at the beta energies that come out. I look at the energy and normalize it to the Q value. So I will get a number from 0 to 1. This is ordinary 2 neutrino double beta decay. And this has been observed for several nuclei, a nice spectrum like this. But then if you begin to see events pile up at the Q value, then you can get your first class ticket to Stockholm. Okay? Because the moment you do that, if events start piling up here, it means neutrinos were not emitted. That means the 2 betas carry all the energy, and it's this diagram rather than this diagram. Right? So that is Majorana neutrinos because of this argument. But in fact, there's a theorem. This is a very highly cited PRD paper called the Schechter-Wallee theorem. If neutrinos double beta decay occurs, there exists a way to convert an antineutrino to a neutrino, a Majorana mass particle. So this is this basic diagram, but you actually don't care what this box is. The black box doesn't matter. The fact that you start off with an antineutrino and end up with a neutrino means you have Majorana neutrinos. Okay? So it's very important to remember that this black box, because one of the exciting things for theorists is the fact that it's unlikely that you just have this so-called Majorana mass term for neutrinos double beta decay, because there are all kinds of new mechanisms you need for mass generation, Majorana mass generation, and that will generate a very more complicated black box. Okay, so no caveats. If you see neutrino-less double beta decay, you have proven neutrinos are Majorana. Okay, so now experiment. Typical 2 neutrino double beta decays are extremely long. You can do a hand waving calculation, you get 10 to the 20 years. So this is a very complicated calculation because of the nuclear matrix element is involved. You have a phase space factor in a nuclear matrix element, and then this eta is where the particle physics lives in the black box. You typically do the calculation for this to be light neutrino exchange. This is, it goes like G Fermi to the 4th, axial vector coupling to the 4th times mass of the electron to the 5th. For light neutrino exchange, this eta is connected to this so-called M beta beta, which is the first row of the PMNS matrix. So the other attractive feature is if you believe in the light neutrino mass exchange as the main mechanism for double beta decay, then you also measure neutrino mass. Okay, and so that is, unfortunately, look at this. If M beta beta is 1 EV, is 10 to the 24 years, 100 milli EV, 10 to the 26 years, 10 milli EV, 10 to the 28 years. So this is ridiculously long lifetimes, extraordinary experimental challenges. But there are a very large number of BSM theories that give rise to higher dimensional operators. The famous 5-dimensional operator is the neutrino mass exchange mechanism. And lambda here has to be 10 to the 15 GeV, so, gut scale. So this is the picture of various experiments. It's typical to show M beta beta versus the lightest neutrino mass. This is the so-called inverted hierarchy, and here's the normal hierarchy. Experiments are trying to get down like that, and that is shown here. These are experiments that already ran. These are experiments that are designed or being proposed. The goal is to try and get below the inverted hierarchy, so you can at least, the idea is that if the neutrino mass hierarchy is inverted, you must see double beta decay by the time you design these experiments. That's the idea. Unfortunately, these experiments, and in fact, I am part of the NEXO collaboration, US nuclear physics funding uncertainties make it unlikely that all these experiments will get done. Legend 1000 is going ahead, but NEXO is stalled at the moment because of lack of funding in DOE nuclear physics. So this is sort of the the summary of the 3 experiments that are considered viable at the ton scale. You have to use scintillation, ionization, and phonons. You use linear combinations of the two. Nexo is a liquid xenon time projection chamber. Legend is high purity germanium crystals. Cupid is scintillating crystal bolometers. These two are at LNGS in Italy. Nexo we were hoping to cite in SNOLAB. But as I said, it's stalled at the moment. That's where it's at. So I'm going to stop there on double beta decay and go on to another symmetry search that we are doing in the world, and that is charged lepton flavor violation. Now, lepton flavor means electron to muon, muon to tau, or electron neutrino to muon neutrino, right? Neutrinos have mass, so individual lepton flavors are obviously not conserved. We've seen neutrino oscillations. Therefore, lepton flavor violation occurs in charged leptons too. We believe that. Now let's do a calculation. That means mu to E gamma can happen. Okay? So muon, then inside in virtually you have neutrinos oscillate here, and you end up with mu to E gamma. So theoretically possible now in the standard model. However, you do the calculation, and you end up with neutrino mass squared over MW squared. That's a tiny number. 10 to the minus 54. So you're not going to see it. It's possible, but you're not going to see it. Branching ratio is 10 to the minus 54. However, the moment you put supersymmetry in there, boom, 10 to the minus 54 goes to 10 to the minus 15. That is barely possible in a really hard experiment. So this is very exciting, right? The moment you see anything at all at this level, you know it's new physics. Okay, so that's why, and then there are these higher dimensional operators that you get sensitive to. You can also look for this in colliders. You look for tau, mu or tau going to E gamma, E plus, E minus, K long going to mu E. These are all charged lepton flavor violating processes that people are searching for to look for these kinds of higher dimensional operators. So these are the, there's the MEG experiment at PSI, mu to 3E experiment at PSI, mu to E in COMET, going on at Fermilab and JPark. There are also tau processes. I'm not going to go through this. This is just so you are aware of these kinds of experiments, why they're being done. Okay, so I won't spend much time on this. It'll be there for you to look at later. I will spend time on this amazing experiment that is being done at Fermilab called mu to E. The idea here is you bring muons to a stop in an aluminum target, and you look for 105 MeV electron coming out. So it's just like double beta decay endpoint of the muon spectrum when muon is captured inside a nucleus. Okay, so if you see 105 MeV electron come out, you have charged lepton flavor violation because you've gone muon to an aluminum target going to electron plus nucleus. Okay, so muon goes to electron. So you have to look, but you need to find an electron that has exactly the mass of the muon, because the muon is at rest in this right here. So what is amazing about this experiment is you want to get down to a 10 to the minus 16 branching ratio. So you need to produce 10 to the 11 muon stops in this per second. It's a ridiculous idea, but this was invented by a Russian back in the 70s, this so-called superconducting S channel. You start with an enormous proton beam hitting a large target. You make a bunch of pions. They go swirling around here. And then in an S channel, the pi pluses and pi minus will actually separate in the vertical. And then you have a collimator, and then you sign select to a mu minus. And then you bring it along, the pi pluses decay to, pi minuses decay to mu minuses. You bring the mu minuses stop here, and then you have a bunch of tracking detectors here. So this experiment is being done. These are extraordinarily complicated. This is a magnetic bottle. You can see here that the magnetic field is graded so that the particles are forced to channel in this direction. It's called a magnetic bottle. So yeah, graded solenoid directs low momentum particles, et cetera, et cetera. And then you're looking for the signal here. So you have ordinary muon capture, You're supposed to see nothing here, and then you're supposed to see this signal. The problem is that if you look at a log scale, this is not nothing. There are extraordinary radiative corrections that make lots of events here. So it's like looking at the endpoint. There are like fourth order QED calculations that have been done to get this act, right? Okay, and that's where the signal you're looking for. Okay, so there are other experiments going on, MEG2, LHC, Bell, CERN. This is in Japan. This is a PSI. This is in Japan. So these are all people looking for charged lepton flavor violation. Okay, so this is just a history of all charged lepton flavor violation. The reason I put it here, these are the new experiments trying to get down here. This is by year, how much we have searched for this. And the reason I put this up here is that the EIC can compete here. And I might have time to say something about it next year by looking at tau appearance. Okay, but I won't say much about this. I have 15 minutes left, and I've got a few more things to cover. So I'm going to go, unless you have questions. But this is essentially showing you various decay channels and where we are in the world in the limits that we have increased. And all these experiments are looking for these kinds of channels. Okay, EDMs. So permanent electric dipole moment of a fundamental particle. So a renormalizable field theory, such as the ones that describe strong and electroweak interactions, conserve CPT. That means masses and lifetimes of particles and antiparticles are identical, etc. But we know CP is violated, and therefore that implies T violation if CPT is conserved. And so one way to look for T violation is a CP violation. And again, more motivated by looking for new sources of CP violation, is to look for a permanent electric dipole of a fundamental particle. So if you just remind yourself, a magnetic dipole is sigma dot B, an electric dipole is sigma dot E. Magnetic dipole is P even and T even, but electric dipole changes sign both with parity and time reversal. Okay, so for a fundamental particle to have an EDM, both P and T must be violated. So if you see a neutron, an electron, if you see, or a quark, if you see an EDM, then you have shown T violation. Can't have an EDM be unless T is violated. Okay, in the standard model, because of the quark mixing matrix phase, at 4 loops, there is a non-zero EDM for the electron. Okay? It's 10 to the minus 38 E centimeters. Now, the current sensitivity of experiments is about 10 to the minus 28, 10 orders of magnitude worse. But 10 to the minus 28 is to tell you that something the size of the Earth has a wobble due to the electric field the size of a human hair. That's sort of the scale we are looking at. I mean, it's kind of ridiculous. Okay, 4 loops in the standard model, but the moment you put SUSY in, boom, you lose 10 orders of magnitude. And that's the interest in trying to do current sensitivity, is that again, you are sensitive to TV scale physics, higher dimensional operators. Now, there's a lot of theory that's required apart from heroic experiments to get to the fundamental EDM to the actual nuclear, atomic, or molecular EDMs that people are looking for. Requires a whole bunch of theory. You start with particle theory, then QCD, then you have nuclear theory here, unless you're doing the neutron, which is easier. Then you need atomic theory as well. So there's a lot of theory that goes in to go from the fundamental EDMs you're looking for to the EDMs you measure. Okay, so this is just to give you a sense that theory is very important here. So these are kind of various things. This is a tabletop experiment, Mercury EDM. This was done at the University of Washington. It holds the record. The basic idea of all these experiments is you put a particle in a B field and an electric field, and then you let it precess. And then you flip the electric field and look for a precession change. So you're flipping back and forth, something we are very used to doing here in the parity violation program. And then you're looking for a difference in the precession frequency. It's always about frequencies. So you're looking for the the difference between two frequencies. And that's proportional to the EDM and the electric field. So it's extraordinarily challenging to do this and reduce systematics. So this here is a tabletop mercury EDM experiment. This here is radium-225 looking for a atomic EDM in a trap. This is neutron EDM at Los Alamos, where they bring cold neutrons to a stop, and they're looking for a neutron EDM, again, all doing the same thing here. Okay. This is sort of where things are in the world in terms of how hard they're pushing. So the planned and ongoing CP violation searches, there are experiments that are tabletop, there are in accelerators. FRIB has a program. Several next generation CP violation experiments on pear-shaped nuclei inside of molecules are currently being developed. The idea is to push towards a standard model prediction. So this is going to be pushed again for the next decade or two. I keep trying to push this to try and see if we can find TeV scale physics and get to the standard model prediction. Okay. So finally, dark matter. So I'm going to say very little about it, but I just want to say that there are all kinds of indirect reasons for why we think dark matter exists. You know, galaxy rotation curves is a famous thing right here. Without having additional matter, you can't explain it. Galaxy cluster, bullet clusters is a very dramatic way to show that, in fact, there must be other matter when two galaxies go through each other. Cosmic microwave background, of course, is our most important and most compelling kind of proof that we think there is dark matter out there. So there's a large body of indirect evidence. I emphasize indirect evidence, and I emphasize astrophysics cosmology. So I'm smiling here because it's up to atomic and nuclear and particle physicists to ultimately directly show that they are correct, because this is all indirect. Okay, so dark matter can be anywhere. So I just showed this one cartoon from 10 to the minus 20 eV to the Planck scale. We are focused here because it's kind of a lamppost attitude. This is a place where we can search. But there's another reason why we're searching in this region here between GeV and TeV, is that a particle with V-scale mass and weak coupling can obtain the correct dark matter density. It's called the so-called WIMP miracle. Okay, so it's an attractive solution to simultaneously solve dark matter particle origin and puzzles regarding electroweak symmetry breaking. So it brings particle physics and cosmology together, and that's why we're looking for WIMP scale dark matter. And so that's the biggest thing. The basic idea is that you have a WIMP, GeV to TeV scale WIMP. It goes and recoils at the nucleus. And that's what you're looking for. There's a large ongoing program, direct protection of the LHC, direct detection, underground detectors. Next phase is so-called Gen 3. They typically show this dark matter nucleon cross-section versus dark matter mass. And this yellow line is called the neutrino fog. What is the neutrino fog? Solar neutrinos come into your underground detector. They're not going to be stopped deep underground, and they scatter and give you recoils. And that's the neutrino fog. Okay. So once you get to this point, if you see a recoil, it can be either due to dark matter or due to solar neutrinos. So it becomes a problem. So this is kind of the final Gen 3 experiment. We'll push down here, and then they'll give up. That point. Okay. Now, there's also funding. The dark matter experiments in the US are stalled. The next phase will require multiple countries to band together to consolidate funding. That's kind of ongoing right now. Okay, so I also show this. This, I think, will be the focus of your topical lecture next week. So I won't say much about it. But there are also light mediators for dark bosons that we look for. And Jefferson lab contributes to this parameter space. And the idea is that the standard model is a portal to the dark sector, and through mediating through a light dark boson. And so there's this epsilon parameter here that you're trying to push down on, along with the mass, which the golden scale is between 0.1, 0.01 to a few GeV, all right? So this is the realm of accelerated experiments, including Jefferson Lab, and I'm fairly certain that you will hear about this next week. Okay? All right, so I just want to summarize here kind of things I've talked about. Some of these things I've talked about, some of the things I'll talk about tomorrow is higher dimensional operators that you're sensitive to. All of these are these 6-dimensional operators with different initial and final states. You're looking for all of them. So, violation of lepton number, violation of time reversal symmetry, violation of charge lepton flavor, flavor changing neutral currents, and then flavor conserving neutral currents. And that will be the focus of tomorrow. Okay? So that's the summary slide. There is a worldwide effort to search for BSM physics. Neutrino physics is an important component of that because we believe neutrinos are a good portal to look for new physics. Pursuing a better understanding of neutrinos is an international endeavor. The search for Majorana nature of neutrinos is one of the highest priorities for reasons I hope I have convinced you. All approximate symmetries are being scrutinized, challenging experiments are being carried out, indirectly accessing energy scales much higher than colliders. Even more challenging next generation experiments are being designed. Dark matter remains completely elusive, and new experiments are being designed to search with greater sensitivity. All right, thank you.
Thanks.
So we have time for discussion, right? Yeah, sorry.
That's what I was going to say.
Oh, please.
Questions?
Hello, I have a profoundly naive question. So people always talk about like neutrinoless double beta decay. What distinguishes people talk about like double beta decay in general. What distinguishes double beta decay from just like two unrelated instances of beta decay?
No, so unrelated instances of beta decay can happen, but they have to happen within nanoseconds of each other. So the probability is just extremely small, that's all.
Okay, that makes sense.
Yeah. That's all. And because you have location in your detector, so you have a big vat of, say, liquid xenon. They have to happen in the same place, right?
Oh, yeah, so you see a position tracking
Yeah.
and also.
So for example, it's actually not such a trivial question. A beta, 2 MeV beta in liquid xenon will travel a few millimeters before they come to a grinding halt. And so you know that the beta cluster will be localized. So if I have, within 2 nanoseconds, I have 2 blobs at 2 different parts of the detector, then you know that they are not from double beta, neutrinoless double beta decay. The oldest student in the audience.
We never stop being students, right? So you mentioned Susie. You called up Susie a couple of times. That it brings you into measurement realm of possibility. How does that interplay with the fact that the LHC has not sent Susie?
Yeah.
Or vice versa, right? If we do these measurements, how will that play towards the next?
Yeah. So Susie is often used as a phenomenology substitute for any new physics because a lot of new physics will have new bosons and fermions that are similar to Susie particles. What is powerful about Susie for phenomenologists is that they know how to calculate in Susie with radiative corrections. And therefore, it is a perfect foil to do a new physics calculation. That's why people pursue it. But at this point, so many parameters in Susie space have been ruled out. But Susie is a standard example because it is a calculation that you can do. Every other higher dimensional operator that you come here you need to come up with a systematic theoretical calculation. And typically you end up with theoretical challenges to try and come up with a reliable calculation if you're just taking arbitrary higher dimensional operators. So it's just a convenient framework to do a phenomenology calculation. Typically people do the SUSY calculation, and then they try to make sure that their SUSY model has parameter space left over from all the indirect searches at the LHC.
See. Thank you.
I had kind of like a general question with these like search type experiments. I guess is there, for each of these experiments, is there a way to determine like this is how long we would have to search, or this is how detailed we have to look in order to rule it out?
Yes. So, so typically what we do, and I think I remember it is in this slide here, for example. You figure out what your goal is for what EDM limit you have. Then you look at your current parameter. It says 10 days, for example, right? So that's how long you got to run it. Now, in reality, 10 days will be like 3 or 4 years, because these are like 10 perfect days when everything is really working exactly, and then you got to do all the systematic studies and so on. But this is a kind of a typical, at the beginning of an experimental design, that you have to do to try and figure out what your uncertainty is on measuring this D, which is your non-zero electrical dipole moment. And so this same exercise is carried out to any search. Right? Yeah.
I had a question about the neutrinoless double beta decay. So I could see from the chart of the upcoming experiments, you have 5 nucleides there that were chosen, presumably because they have a possible double beta decay, but no single beta decay.
Correct. So it all starts with this, where was it? Was it before? Yeah, before, right? Here. So first of all, you got to choose one of these.
So are those the only nucleides that meet that criteria?
Yeah, this criterion plus Q value high. So if you go, first of all, remember, everyone needs to understand what 10 to the 20 half-life means, right? I'll give you an example. We ran an experiment in Carlsbad, New Mexico with 100 kilograms of liquid xenon. The 2 neutrino half-life is for xenon 136 is 10 to the 22 years. That means in a 100 kilogram vat of liquid xenon, we see a flash from ordinary double beta decay every 10 or 15 minutes. If I take my fingernails and put the detectors that measure double beta decay in this experiment, I will get megahertz response from my fingernails, from the uranium and thorium in my fingernails. Okay, so that is the kind of cleanliness that you need to get at this level, right? So that's the first thing. And because of that, you're keeping the Q value high because the energy of the uranium, thorium, and fingernails is typically below 2 MeV. So you want to be above 2 MeV so that you are reducing the amount of ordinary radioactivity that you're going to see around you. Okay, so that's the cutoff that has been made here. This is candidate with Q greater than. If you go through the nuclear chart, there will be a lot more with Q less than. Now, that's the first step. The next step is the R&D that we started doing in the late 1980s all the way to now is now systematically go through this. Each one of these, the experiment depends on chemistry, and where you are in the nuclear chart has nothing to do with this. It's all chemistry, right? Because xenon is a gas. Germanium is a semiconductor. Tellurium is a bolometer. That's why you use those things. Tellurium makes a good bolometer. Germanium makes a good semiconductor. Xenon makes a good EPC. And so the chemistry of these nuclei decides your experimental technique. So all of these were pursued starting in the late 80s. And then slowly they were eliminated as being too hard. And what survived is this, after lots of research to go to the ton scale.
Okay, thank you.
It looks like there aren't any more questions. Oh, there is one more.
There's no other questions. You showed a plot of experimental precision versus time.
Or,
I forget.
oh yeah, for charge lepton flavor violation. Yeah, that's just showing you that people have been looking for this for a long
Yeah,
time.
all right. So
Because mu to E gamma, as soon as the muon was discovered, people wanted to find mu to E gamma.
So does it mean that we've reached a limit on our?
Yeah. So this is the
techniques?
point, right? This is to show you that we are now struggling to go here. But these points are actually on this curve past 2030. All these experiments are being designed to take data in 2030 with this sensitivity. So this is part of the curve. So,
So what are they doing better than the ones in 2010?
well, or you can say that this is looking rather challenging to do because we are breaking the.
Or that? Yes. Okay, so, okay.
These are extraordinarily hard experiments that are being funded, and we are cheerleading them on, but they're hard.
But experimentally, do they have a new technique or are they just improving systematics from previous days?
Some of them are new techniques. Some of them, mu to E is a brand new technique, right? This S channel thing.
Yep.
It's a extraordinary experiment.
Okay.
If Moeller hadn't been approved, I probably would be doing that. I was part of it when it started. It started in the mid 2000s, and we are finally finishing construction. Chris Pauly is the project manager.
All right, thanks.
I have a naive question, like for the double beta decay, how you can like distinguish like a one beta decay or double beta decay like in the experiment?
Well, you do not. It's just that if you're pure xenon, double beta decay is for single beta decay is forbidden, right? That's why you choose xenon 136. So first of all, natural xenon has xenon 129 all the way to xenon 136. So first you need to isotopically purify to xenon 136, right? So I'll go back here. I need xenon 136. So that I know is, first of all, xenon is a stable gas, right? So the fact that xenon 136 in fact decays is an extraordinary thing. And until we discovered it in this Carlsbad, New Mexico experiment, no isotope of xenon had ever been shown to decay, right? Because xenon is a noble gas. It doesn't decay. But xenon 136 has this extraordinary rare possibility. But obviously xenon is even xenon 136 is considered stable because it is a 10 to the 22 year half-life. Right? So there is no single beta decay happening in the experiment.
Thanks.
I don't see any more questions now. Okay. Well, let's thank Krishna Kumar again then.